My name is Wally Towner, and I am a professor here, not a full professor, but I'm a professor anyway, in the School of Business here at WPI. And so my background is I have a mechanical degree from here and a master's in IT, master's in manufacturing, and a PhD in manufacturing that I earned recently from Professor Brown. I also went to Babson. I have an MBA from Babson. I attended Harvard Business School in the Owner-President Management program. So I'm like one of these hybrid people. When I graduated from engineering school, I went to work on my family's manufacturing company. So I can weld, I can run CNC machine tools, and make stuff to fix my car, which is really cool. But I also know how to do accounting, which is kind of cool. So I teach a lot of courses in the School of Business, and I have been increasingly bringing the axiomatic design framework into my business classes. I'm currently teaching a course in global operations strategy. And since I think it's kind of hard to be an expert in global operations strategy because it's so broad, then my approach has been, well, let me teach you how to think about how to put a strategy together, and then you can populate it with whatever global operations you want to. And so the students I seem to be happy with that approach. And some of the things that in fact, I lectured last night, Professor Cochran. The students have been submitting axiomatic design decompositions made in a Claro in groups. And so last night, they were sending me the beginnings of their global operations strategy. And so some of the questions that I had for them were, when you make up an FR, how do you know whether you've achieved it or not when you put your system into operation? And so one of the top level FRs that we had was design a global operations strategy. That was a top level FR. And I said, well, that sounds kind of like a yes-no question. And I think that if we're going to operate a business or some kind of an engineering process, it's more of a matter of degree. What was our sales percentage? What was our market penetration percentage? What was our profit percentage? Not, did we make a profit? Yes, no. So that kind of takes away from trying to structure complex problems when it's in a yes-no situation. And some of the advice that I had given them was that it can be easy to tell whether you're doing a good job on the decomposition or not, because if you take the posture that someone that worked for you or that you were in charge of or you were managing brought this to you, you would ask them, well, how do you know you achieved the FRs? And if there's not an objective way to be able to tell how you achieve the FRs, then I think you need to do a better job writing down what the FRs are. So hopefully that lines up with some of what you've been learning in the previous session. And I've also, continuing in that vein, in my decompositions, I increasingly add columns that have measurements in them. So if I were to put an FR, I want my car, I want to have a very fast car. And a measurement would be, well, if the car went over 100 miles an hour, then I would consider that it would be successful. And if it went a lot over 100 miles an hour, then I'd know that I really had been very successful. And so you can put ranges on these things and give yourself a way to try and measure, have I achieved the FR? If I haven't, how far away am I? If I've exceeded it, how well have I done? And kind of put a metric on there. And it helps think about how to build the FRs. So this tutorial is, I think you'll have some fun with it. We're going to take some pretty simple FRs and DPs and build some matrices and see what we can learn. So when we're building an axiomatic design matrix, one of the things that we might be concerned about is if my FR is what I want to achieve, my DP is how I'm going to achieve it, would it be a good idea if my design parameter fulfilled more than one FR at a time?
No.
No. And why would that be? Because you have coupling. But that's just a word. What's coupling mean?
Trimming, more adjustment.
Yeah, you can't independently adjust all the different parts of the design without affecting other things.
You lose money.
And you
lose money.
cost you money. It absolutely can cost you money. But for example, well, I'll give you some more of those as we get to them. And so we might want to answer some questions. What's the best order of adjustment to adjust the DPs to get the FRs? We might not know what is the most important one because we don't have a good way to understand what DP affects which FR. How do we know if the design satisfies Axiom 1? What does Axiom 1 say? Maintain the independence of the functional elements of the design, which is a good thing. Do we always have to maintain the independence of the functional elements? What if we don't?
There could be some FRs that say no.
Okay, if one of the ways to think about this is that sometimes FRs can actually be coupled and it's not a bad thing. And I'll explain that in a little while. So for example, one of the examples I'm going to give is if I am the accrediting body for the engineering schools known as ABET, and I come to WPI and I say, well, here's all these things engineers are supposed to be able to do, add, subtract, and work in a group, and all these other things. Well, it might be good that we can add, subtract, so we can solve problems and do design. And so the DPs that solve those FRs can actually have one DP satisfy more than one FR, and that's not necessarily bad from the sense that we want to produce engineers that have broad skill set that fulfills all the FRs that ABET says we have to have. But what might be bad about that is we might have duplication of effort or resources in that design. So even though it's acceptable to have a design parameter fulfill more than one FR, we may not do it as efficiently because you're having the same information show up in different courses. And well, I already learned this, not going to learn it again. Well, reinforcement's good, but then there's a point where you have diminishing returns. And so maybe we want to just have a better handle on what the DPs are affecting what FRs. Okay, so can we minimize non-value added iteration in our designs, which would be good, and which components should be detailed design first? What should be designed first? Probably the most important thing in the design. But how do we know what is the most critical part of the design? What's the most important part of a design in axiomatic design?
Function.
Function, okay. Is the top level more important than level 1 or level 2 or level 3?
At the end of the day, it is.
Yeah, I would argue that whatever your FR0 is determines the likelihood of you successfully building out a design. If the top level FR is not accurate, correct, on point, you'll actually solve a different problem than you intended to solve. And so one of the things I find when I have students make up axiomatic design decompositions is that they spend more time on getting that top level FR right. We're all pretty smart people except for me in this room, right? Everybody else is smarter than me. You can solve any engineering problem that gets put in front of you. You solve any business problem that gets put in front of you. The problem is determining what the problem is. And so if you don't get that FR0 right, it's difficult to have the rest of the functional requirements be proper, that when you add them all up, they equal what the top level FR is. And so you wonder why there's a lot of government and corporate programs that don't go the way they're supposed to go, and then ultimately you find that, well, you know, what we thought was the problem we're trying to solve is not actually the real problem. It's this other problem. Well, we needed to put more time into deducing that. So here's an interesting thought experiment. I think I got, did hierarchical design thinking help to create the United States of America? We owe our existence here in this room and the 50 states and the lovely form of government we have to hierarchical, parenthetically axiomatic design. It sounds like a stretch.
I can say yes.
Well, here we go. So back in the American Civil War, steam power was able to decouple your ability to move and separate you from the wind. So prior to that, you think of Admiral Halsey and the ship of the line and the French and the Spanish galleons, and they're out there on the high seas, right, and they're fighting each other. And if they're getting into a battle, then they all had to line up in a row, and the other guys all lined up in a row, and they passed by each other and they shot all this stuff out. And then if the wind changed direction, then they would really mess their plans up, and they had to go get in a different line. And so the direction of fire was essentially determined by the direction of the wind. So along comes a steam engine back in the 1700s, used to pump out water out of mines in Scotland, and then someone said, well, let's make a small one and we'll put it on a boat so we can go water skiing back then. I don't think they did that, but anyway, so they put it in a boat, and now a boat could actually move across the ocean independent of which way the wind was blowing, which is a huge benefit. And so this is all around in the mid-1800s. I don't know the exact year. And so the southern part of the United States had a boat called the Virginia, and the northern part had, their boat was called the Monitor, which is also known as the Merrimack. And so you got this ironclad vessel. Well, you weren't around then.
I said it was the other way around. It was the Virginia that was the Merrimack, the Monitor.
Oh, the Virginia was the Merrimack, and the Monitor was the Monitor.
So it was the Monitor.
I'm an engineer. I failed history. And so someone got the idea, wouldn't it be really great that instead of being the ship of the line back in Admiral Halsey's time where I'm able to fire at you because the wind's blowing a certain way, I want my gun to be able to point in some other direction. And so they decouple the direction of fire from the direction of travel by putting a swivel turret on top of the Monitor. And so this was a new FR that was developed by the Union side of the equation. And they said, well, we want to maximize the independence of the functional requirements of this boat we're in, one of which being we want it to be able to travel and steer it, and the other one is we want to be able to fire it in any direction that we want. And so following with this, steam power decouples locomotion and wind, and the swivel turret decouples the direction of travel with the Monitor. And so if we're looking at these two vessels, we've got 6 times as many guns in the Virginia. It's 50% faster. It's 4 times as big. We know the Virginia's going to win, right? And I would advocate maybe we want to run away. So the Virginia comes into Hampton Roads. There's a body of water that's south of Baltimore, I guess, in there, and starts to wreak havoc. And the Monitor shows up and starts to fire on the Virginia and moves around all afternoon until the Virginia gets tired of trying to get the boat lined up in the right way so they can hit them, and they go away, never to come back again. So this is kind of a famous painting or of this battle. And so this is axiomatic design, hierarchical thinking, axiom 1, maximize, maintain the independence of the functional elements of our design at work, of which we are now the descendants here in the United States of the benefit of this thought process, which is kind of cool. It's a little stretch, but it's kind of cool. So as we go through our design lives, are we going to be able to recognize opportunities that we now are able to decouple FRs or come up with new FRs so that we have our designs are able to fulfill new functions that were not able to be perceived before? You might get that opportunity. So when we start to put a matrix together to see what this looks like, The design matrix for the Virginia, as far as FR1 being adjust the direction of travel and FR2 adjust the direction of fire, these two things are coupled. So it's really difficult to adjust one or the other without affecting one or the other. And if you look at the monitor, the rudder controls the direction of travel, and the turret controls the direction of fire, and the 0 indicates that there is no influence, essentially, between the turret doesn't affect the direction of travel, and the rudder doesn't affect the direction of fire necessarily, because that's not 100% correct. The rudder does adjust, does have an impact on the direction of fire, but not to the degree that the turret is able to overcome that. And so each FR in your design should have its own design parameter. Do you have any questions on this? What's really fun about this is it's so intuitively obvious and simple that when you actually put it in the design matrix, you go, oh wow, that's actually really cool. I think about it that way. And Axiom design, as you probably have already been made aware, is you're able to take this hierarchical thinking and go multiple layers deep down and solve very complex problems because essentially limited by whatever method you use to be able to make your design matrix. Okay, so this is another interesting story about maintaining the independence of the functional requirements. So this came from the axmacdesign.com website. Back in 1625, the king says to Hendrik, I want you to build me a boat because I'm the king. And the last boat that you built me was 108 feet long, but because I'm really a super duper king, I want it to be 120 feet long. And the other one didn't have enough guns on it. So we need to have an extra deck with more guns on it. And this is going to be the greatest boat ever. And so Hendrik builds the boat and goes out, mile offshore, rolls over, wipes out the crew. And so some of the lessons are that when you're looking at the functional requirements of your design, a lot of it's experiential based, but not necessarily understood well why things happen the way they happen. And it's difficult to capture the essence of how the designs function and why. And you also have the issue of not being able to make a cogent argument to the king why it's not a good idea to put a third layer of guns on top of the boat. There's another way you could think about this in that I had found somewhere in biblical times that the way you became a good house builder was that the houses that you built didn't fall down and kill anybody, because if they did, they killed you. And so there's a great impetus to make sure we understand why we do something from an engineering point of view to achieve a functional requirement. So this boat actually exists. They found it in 1967, I think, and then they raised it in 1997, and it's in a museum over in Sweden somewhere. And it's just a great example of not understanding the functional requirements and the design parameters and how they interact. This is a faucet that happens to be in the men's room on the second floor of Washburn, if you're wondering. And so I have a question. Is this a good design for a faucet? Previous undergrads are not allowed to answer this question. Is this a good design for a faucet? No? What?
But it's an adequate design.
It may be adequate. It may be adequate, but could we improve on it? What's bad about it? Well, let me ask you, what are the functional requirements of the faucet?
Flow and temperature.
Flow and temperature. Can we get flow out of that?
Sure.
Can we get temperature control out of it?
Sure.
Can we control those two things independently? No. And so we have to iterate to get the right flow at the right temperature. And so from a purely functional point of view, does the water come out, it's hot water? Yes, we can do that. And this is a simple engineering problem, but if we had a more complex problem, it may be very expensive for us to iterate this. This could be a component inside a machine that makes semiconductor equipment. And we don't want to be iterating to get our flow and temperature right. We want to be able to have those two things be independently controlled. So if we look at, so we just discussed what the FRs were. If we look at the design matrix for this matrix is fully coupled. Both design parameters influence, affect, and control both functional requirements. And so we might be able to get the desired level of flow and temperature, but it would be a complete shot in the dark to be able to get that first time right out of the gate. And so you think about the delta faucet you might have in your kitchen. You control temperature right to left and control front to back, and you have independent control of those two things. That matrix is not coupled. There's another very simple example. I'm going to design a vacation. So my FR1, I want relaxation. FR2, little romance. So for relaxation, I'm going to use ethanol, otherwise known as, something at the bar. And for the romance, get a little dancing, but the ethanol actually impacts the dancing. Probably not in a good way if there's been too much ethanol. And so we might need to have a new DP to satisfy that FR. So we will substitute yoga, and we'll get the romance independent through the dancing, and the yoga will give us the relaxation and have a better vacation for it. So this information comes from my dissertation, which I completed recently with Professor Brown. The title of my dissertation was The Design of Engineering Education as a Manufacturing System, which was really kind of fun, because when I actually went around WPI and met with some of the professors, they were actually really upset that somebody thought that they could make a manufacturing system out of engineering education. They didn't like that, those two words being in the same sentence. And so the way that dissertation structured, there's a chapter to determine what value is, and the value is if you go to school and pay $50,000 a year for 4 years, put some time value of money equations in there, and find out that you're going to get a job making a certain amount of money at the end. Well, the sooner you can go to work at a given level of pay, then one degree is going to be worth more than another, theoretically, all things being equal, right? So we could graduate in 2.5 years instead of 4, and I could go to work sooner. Or maybe I could get 2 degrees in 4 years and be worth even more. So there's a little chapter on that. And then the next chapter was on manufacturing system design. And I used the axiomatic design process to work through this. So the basis of my decomposition, based on manufacturing engineering principles, which Professor Brown had written a paper on this not that long ago, that said for all manufacturing problems, the top level FRs are maximize the value added and minimize the cost. So I'm thinking that any manufacturing problem you have, that probably are the 2 top level FRs. I don't know, and we would all love to hear somebody that has ideas that would be counter to that, because it would be important. Professor Cochran, you have other ideas.
Well, I don't, it's the age-old debate of whether minimizing cost is an FR or whether it's a constraint. So that could lead to some debate.
Agreed. But if you're operating a factory, you certainly would want to make the most of money you could, implying that you need to find a less expensive way to do things, right? So I think that Go ahead.
What about a couple of things, like for instance, when I grew up in manufacturing, that was a bad thing to say. It was maximize the quality, and therefore if you maximize the quality, the better the environment, you'll minimize the cost. So what about the coupling of that both? Like,
Okay, well when we say maximize value added, does that not imply that the value added to the customer is driven by giving them the most amount of quality that you could? So you need to have a way to define value added, actually. You know, you can define that. But if the customer views you as being the highest value added, independent of what it costs, and then you as the producer are able to operate in such a way that you're able to maximize your own profit off of the manufacturing process, then I would think this would be an ideal situation. So if you put Apple in there, and you got the iPhone going on, or the iPod, this is not sales price now, this is just operational stuff, right? They have relatively low operating costs versus if they try to do it in the United States, at least that's the argument. And they also have very high value added to the end user. And so looking at Apple as a manufacturing concern, I think we can kind of get a good idea of how this might play out. But I would say that over the next few months, if you're thinking about this, I'd love to hear what you have to say, because this is really a starting point, not an ending point. So when I made my FRs up, I said, okay, well, I'm in engineering school that kind of might look like WPI. Then I turn out engineers. And my product actually is engineering students. The students are not necessarily customers. They kind of are customers because they benefit from the process, but they're parts that are being converted along the way. And they get value added over a period of time. And if we can add a lot of value in a shorter period of time, then the conversion process has more value to the student. And before I get anybody upset at me, this has nothing to do with whether you play sports or be involved in student government, which has lots of value, join a fraternity, that's really important stuff. The issue is, how would we make the degree more valuable, give the students the opportunity to reduce the non-value added portion of their education, of which there's a lot that happens in between when they get information given to them. And so that's the maximize the value added part. The minimize cost part is pretty obvious, right? State of Texas says they want to have a 4-year degree that costs $10,000 or something, and the MOOCs are going to take over the world, and everyone's going to go to school for free, and the professors won't have any jobs anymore, and all this talk about the changes coming in education, which there's going to be some radical changes, but probably not quite as fast as everybody thinks, and it certainly won't end up exactly. The whole world's not going to online. I don't want to go and have my gallbladder out by the doctor that learned everything on a MOOC. Not so good. So with these two top-level functional requirements, I looked at how would I know that I added value to my students. And so I have this really convenient guidepost known as ABET, which says for any engineering school all over the world, and generally for whatever particular program, there's 11 things that you need to be able to do. And this is highly contracted to be able to fit on this slide. But you got to be able to add and subtract, work in a group, do all these kind of things that engineers are supposed to be able to do. And then on the minimize cost or minimize waste part, I looked at Taiichi Ohno and took the 7 wastes in manufacturing, of which that's what the top 7 are, and made up an analogous way to view that. And I put 2 extra on the bottom. The school is definitely interested in professors not sitting around looking out the window and want to get, why can't you teach 5 classes at once? That's one of those questions. And then unleveraged infrastructure. So the school is really happy that we're here in the middle of the summer using this room. Why aren't we doing this at 2 a.m. so we could have other people at 2 p.m.? That's another question. But being able to leverage the infrastructure that you have. And so if we look at Axiom 1, to think about maintaining the independence of the functional requirements of this, This is how my matrix turned out. So there's a lot of things missing off the sides. There's just not enough room in the slide. But 1 through 11 is the A-bet material, and then 1 through 9 on the bottom is the minimized waste part, and all the DPs to satisfy them. So I looked to see, well, what DPs are affecting more than one FR? And the way that A-bet writes their requirements for understanding how well your school's performing, they have all kinds of overlap all over the place. They actually say the same thing in 3 or 4 different places. And so it implies there's a lot of coupling between the design parameters that fulfill the FRs and multiple FRs. And so if we were trying to figure out which one of these design parameters to fulfill first, it's kind of hard, because you have a pretty messy looking matrix there with stuff all over the place. And I could show you on the next slide. So this kind of zooms in on 1.8 was, I have a design parameter system for creating knowledge of math, science, and engineering, which happens to be one of the A-bet requirements. And so how does that system interact with the other 11 FRs? So there's actually more than one kind of coupling in our design matrix. Some coupling is intended. So if I look at design parameter 1.8, system for creating knowledge, and I look at function requirement 1.8, we want to learn math and science, and then my system is how to create math and science. That's actually an intended coupling. We want that to happen. We want to make a system where we're teaching math, science, and engineering, and the result is that engineers know math, science, and engineering. So that's a good thing. Sometimes we have coupling that is, it's not detrimental, it takes place, and maybe it's sequential in nature. So you cannot, I don't believe that you can learn how to write before you learn how to read. Did I write on that? I think it's pretty hard to write if you don't read. And so you have this sequential thing or temporal coupling happening. So we learn how to do math and science in our first few years, and then in the later years, as we become more advanced, then that design parameter actually influences how we solve problems and how we do design. So we got this sequential or temporal coupling happening. And I would also say that most times when we think about coupling, we think that we want to maintain the independence of the functional elements in the design, which is true in most part, except that sometimes when there's coupling, it's not always negative in nature. So the fact that the engineers learn how to do math, science, and engineering and solve problems and can do design, there's actually nothing really bad about that. There may be redundancy built into the system, and we're inefficient in how we accomplish those FRs through these GPs. But we might want to know that in advance so that we can make our system work the way we want it to work. Yeah.
FR17, the way it's stated,
Yep.
experiment, I've found that in government programs, they will essentially prescribe something to you, like thou shalt experiment, right? And so the edict by the government becomes an FR for people. But to me, just because they said thou shalt experiment doesn't mean that the government has identified an FR.
I have no argument for that at all. I wonder how the government figures out a lot of things that they ask you to do.
The lawyers typically write the law, and the law is written in the form of DPs. At least that's my way of thinking. They're giving you a rule, so they're saying to educators, thou shalt experiment.
Well, if I could have some license on this.
Sure.
This is very much contracted. DP 1.7 probably has 15 words in it. And it says, engineers should be able to design an experiment, conduct an experiment, and analyze the results of an experiment.
That sounds like an
Right, it is. It is. But this is squished way down, so I could get on the slide. So if you want to go to ABET's website, you could go and find that stuff.
I
Right?
just want, well, we were talking about that earlier, that the ADAT specifies these outcomes.
Yeah.
And the problem is that it's hard to know the origin and the thinking that went into those outcomes that they're specifying. And I think that's true of a lot of government programs.
Yeah. Your government is like science fiction. As you wonder how, the government does not actually always serve a logical choice. There's can be other underlying reasons why things are done the way they're done. And, an engineer would say, I don't agree with any of that, but, the politicians love it, right? And I think we should stop talking about this, because then we'll go into bad area.
But it seems like there's an opportunity, though, to convey what is working in these laws and what isn't.
Yeah, I would say, actually, I have thought that if I were, I live in Rhode Island, which is a really interesting place to live from a political point of view. And if I were to try and figure out an axiomatic design matrix of how I'd want to operate the state of Rhode Island, and I know that what my top level FRs are going to be, they look nothing like what the top level FRs of the people that run the state are. And so therein lies where I think we should stop, right? Because I think we want to help business and all these other good things, right? And the other people say, no, we have to take the stuff from the business and give it to these other people, and we don't want to go there today.
This is where there could be a clash between micro and macroeconomics.
Absolutely.
From a micro perspective, a government grant goes right to the top of the income statement.
Right.
So for an entrepreneur, we want to maximize grants, which might be detrimental to the macro situation of government intervention and how we all have to fund that. But as an entrepreneur, it reduces my cost of capital.
But if I'm in government,
It reduces the amount of debt. And of course, the cost of capital for debt financing is much lower than it is for equity. So if we can...
Rick, if I'm in government, what's my top level FR? Get reelected. Right, so that's not on this. But I agree with you, absolutely. So this is just another example of another DP. Here's what I did with it. I said, okay, well, if I look at all these things that are common amongst all the 11 things that ABET has going on, there's factual knowledge that you can get in books and library that exists. And then there's knowledge of consequences, like I'm going to pollute someone's water supply. You should be able to know that in advance, right? Should be able to, not always, right? And then you have these engineering skills, which is the experiment stuff and the solving. And then there's the communication. And so what ABET says, interestingly enough, and it's not passing judgment on ABET, right? ABET says you cannot be a practicing professional engineer unless you do all these things. So if one thing's missing, you don't actually fulfill the mission. You can be really, really smart and know all this factual stuff, but you can't talk on the phone. So you can't be a PE, right? So they're trying to. And so it'd be kind of interesting at some point. I hope to be able to have someone at ABET actually look at this and say, how they feel about breaking down their FRs in this way, and the design premise will fulfill them, and say, well, if I were designing an engineering education system and I wanted to minimize the amount of redundancy I had in the system, is this a little easier way to address the FRs in the system? So this is one stab at it, right? This is not definitive in any way. But my goal was to deal with that and say, like, all these interactions going on between these DPs and FRs, they're all not necessarily negative, because we learn how to do all these different tasks in different courses. But how many times are we learning them? When you learn the Laplace transform in 4 different courses, well, maybe we only need to learn it twice, and then we use the other 2 opportunities to learn something else, right? Because let's face it, $53,000 a year to come to WPI for the first year, and the cost keeps going up, and the school actually can't increase tuition fast enough to rise faster than the underlying costs, then we need to find a way to be more efficient. So one way we can be more efficient was redesign the education system so that we have the same or better results using less resources, right? And so we're coming up against that. We're living in that right now with the, I mean, when Obama went in his first year, right, when he was running for election the first time, he's, we're going to find out why it costs so much for college education, it's out of control. And the governor of Texas is trying to have a $10,000 degree, and so just a little personal thing that I want to throw in here. I attended a program at Harvard Business School. It was an exec ed program, so I'm an alum, but I don't have a degree, right? Not an MBA from Harvard, right? And the professor, one of the professors who's been there for 50 years, he said, what we do is we increase the tuition every year to see if anybody actually doesn't come. And they still can fill the programs up every year, right? So you have this perceived value that it doesn't matter what they charge, they can still fill it up. And so we have a little bit of that happening in the college arena, engineering school. Why not just keep charging more and more and more? Because the perceived value of return is there, and so therefore we don't actually really have to function as efficiently as maybe a corporation would, because we're able to continue to increase prices in a market that's inelastic, right? When whatever you charge, they'll pay. So you have kind of that thing going on too. But from an operational point of view, I think we want to have our engineer creating factory be as efficient as possible, because what we charge for tuition and how much we operate this and how much it costs to operate the school actually don't have anything to do with each other. We can charge $1 million a year to come to school. It only costs us $10 a year to educate. Then we have a lot of wealthy professors, right? So the value of the product is not connected to how much it costs to produce the product. So Apple's a good example, right? Apple has more cash than almost every country on the planet except for 2 or 3, right? And that's how they did that.
Can you go back to that slide for a second?
This one?
Yeah, why you circled those two?
Oh, because...
They're not in the X's and they're not the two highest.
No, I understand that. 1.1 and 1.8, there's 1.8, there's 1.1. I was just showing that on the following 2 slides, that's where I broke these out. Yeah, they're not...
Okay.
Yeah, they weren't, I wasn't saying these are special anyway. It was just, okay, this is the ones I looked at, Yeah. Yep. Actually, the reason that I did pick these 2 was one of them has, the interactions are all below the diagonal. Right, the one on the left, they're all below the diagonal, and the other one has on both sides. And so that was one reason. And I can explain some more as we move on here. Okay, so now going back thinking about interactions, I'm going to spend just another 1 or 2 minutes here on these ideas, and then we're going to move on. So if you think about FR1 for the school is produce engineers with the highest amount of value added, and FR2 is minimize the cost to operate the system. Well, all we have to do is shut the system down, and we get FR2. We won't make any engineers, but we'll be very efficient. And so there's actually the coupling between my FR2, which is minimize the cost of the operation, is affected by DP1, which is DP1 is produce the engineers efficiently, affects FR2, which is minimize the cost of production. You have to satisfy producing the engineer before you minimize the cost. And now this is based on the second iteration of the decomposition where I reconfigured all the FRs. And if you notice, they're all independent at this point. So you should be, in theory, be able to change any one of the DPs independent of all of the FRs. Because I took away all that coupling that existed just by looking at the original A-bet decomposition. And so as it
Can you explain that? Because I'm lost on that.
okay. So when we looked at this thing, right? down here in the bottom, it shows that this slide may not be actually right. There was a little amount of coupling between the design parameter and the FRs that they fulfilled. Okay, but the original ABET criteria had all kinds of interactions between the DPs and the FRs. So when I made up the new FRs, what's going on with that? I went to 4 FRs. And all these were independent because I combined these things that were kind of like quantities. And then when you put that in the matrix, it ends up, okay, it's much cleaner and much easier to manipulate. All right, so let's get out of there. Go back onto something engineering-wise. So who's read Principles of Design, seen that book, besides David and myself? And so one of the things that Dr. Sue has in this book is that he was examining a reaction injection molding machine that was in some kind of a commercial environment. And the way these things work is you fill one reservoir with a really expensive polymer and another reservoir with another really expensive polymer. And when you press the two together under pressure, then dashboards to cars come out and furniture that goes in your backyard. And this the functional requirements are that we have to mix the correct amount of these two things together for under a certain amount of time and pressure, and then we end up with these parts that we're going to make. And so upon examining the FRs for this system, FR1 was to deliver the liquid at a high flow rate, presumably for, it doesn't say in his analysis why that is. One reason you could suspect high flow rate would mean high productivity, you get a lot of parts. But more importantly, when you mix these two chemicals together, if you do it really slowly, the stuff's going to harden up before you make your part. And that's not going to be good, right? So you got to have this happen relatively quickly. We have to get enough of the mixture into the mold so they don't have voids. And they have to be metered, 2 to 1, 1 to 1, 1.3 to 1, whatever mixture there is. And the way the original machine was set up that was analyzed, right, was we could control the pump speed, which was gave us our pressure in the system, and the nozzle size, which also affected pressure in the system. And so those are the two things that the plastic injection molding people are able to control. And so this is what the design equation looks like. A is a representation of the design matrix, which shows the relationship between the DPs and the FRs. Does anybody have any comments about this particular set of equations? Something unusual? How many FRs are there? There's 3. How many DPs are there? 2. How do we adjust the system if we have 2 DPs affecting 3 FRs? We're back at the sink again, right? All kinds of iteration happening in this. So this gets a little more detailed into showing the matrix on the right side, showing that the DP2 affects 2 of the FRs and DP3 affects 3 of the FRs. And this is almost fully coupled. It would be very difficult to control this design. And so this is a little bit cleaner picture of it. Q is flow rate. We have X is mixing, metering, pump speed. Okay. So we got a violation of Axiom 1. We don't have independence of the functional requirements. How do we fix that? You either have to redo the FRs to get better ones, or reduce them, which actually I did in the ABET example, or we got to add another DP so we have more control in the problem that we're trying to solve. So one of the solutions that's in Dr. Sue's book is, well, we need to have a way to put a mechanism to adjust the combination of the two chemicals in a measurable, known way so that we can control that. And so what they did was they put a shaft between the two pumps, and it's not quite as simple as that because the shaft actually would have a gear ratio in it, right? There's a transmission in there because one could be turning at 3 times the speed of the other, right? But for schematic purposes, this is just showing that these two things need to be connected so we can make a ratio in between them. And so now we have 3 DPs fulfilling 3 FRs. And so if you look at the matrix on the bottom, this doesn't look like any of the previous matrices in that we have interactions between all of the FRs and all the DPs, except that one DP affects one FR, one affects 2 FRs, and one affects 3. And so that would tell us that there's probably an order of adjustment that we have to go through in order to get the system to work right. So would anybody want to hazard a guess which DP we would start with? Probably the bottom one, right? Because it affects 3 FRs. And then once we get that set, then we move up to the one that affects 2. And once we change that, then we're left with the last one, and you set that last. And I think this is pretty common in industry. I know a lot of the machinery that I've operated, it's like, okay, you know, like I actually have personally operated many laser cutting machine tools that cut metals, big sheets of metal. And a laser is really kind of cool because you got this really high power beam of light with a magnifying glass on it that makes a spot. And you have a certain amount of energy that you put into it. And so as the laser is traveling along and it's melting the material and essentially blowing it out of the way, you can either go, you want to go as fast as you can without going so fast that the energy can't get distributed over the thickness of the material and complete the melt. But if you go too slow, then things get too hot and you end up with the edges don't look so good because you have too much energy in one spot. So you're always optimizing how fast you're going versus how much oxygen is injected into the cut, and you're looking for this optimal situation. And so you'll find the operators, as they become more experienced, they'll start out at a known rate and they'll say, well, the thing will cut at 100 inches a minute in 1/8 thick steel. And then they increase the speed 2% and increase the gas 2%. And then they increase the speed 2%, increase the gas 2% until maybe they get to about 120 inches a minute. And if they go to 121, the system stops working and they're not able to cut anymore because at that speed, there's not enough energy to distribute over the material to make the cut be able to be continued, right? And so that's what's happening in this situation is that you're setting whatever design parameter to achieve an FR and get that optimized before you go to the next one. So analogous to that. Okay, so this is a simplified view of that matrix, and we just discussed that. So it'd be nice to have a square matrix. If we have more FRs than DPs, then the design's going to be coupled, which is what we had in the previous. If there are more DPs than FRs, then it may be redundant. You got to figure out what you can take out. If you lose independence, fewer parts is not better. So I'll give you an example of that. One of my classmates that graduated from the manufacturing engineering program a number of years ago went to work for a company that made thermal cutting equipment. And the engineers that were building this machine tool said to him, well, you know, if we could take the motor, the electric motor that runs the pump for the coolant, and put a fan blade on the end of it, then we could eliminate the other electric motor with the fan on it and reduce the part count, and the price will come down of the machine. And And so they tried that for a while, and when it went out in the field, they found that when either one of the other pumps failed in the original system, you were still able to either move coolant through or cool the reservoir. But when you put the cooling fan to cool the reservoir on one end of the motor, and you put the pump on the other end of the motor, when the motor failed, you lost both the ability to move coolant and cool the coolant, which caused things to melt inside the machine. The customers are very unhappy about that. So that red change that they probably saved a couple $100 by eliminating the second fan cost them many thousands of dollars in field service to go back out and retrofit to put the separate fans back in. So fewer parts is not always better. We also don't want to confuse physical independence with functional independence. So if you think about a Swiss Army knife has 10 different things going on, and they're all physically integrated, but every single thing in the knife is actually functionally independent. So you can have physical integration and still have functional independence. Let's think about the FPARs and DPs you made up this morning. Did you make any FRs up this morning? FR, go to Hawaii today. DP, get out of this class. Get on plane. David, you want to help us through this?
Sure.
Well, you suggested that we could start to put a matrix together based on some of the FRs and the DPs.
Yeah, we were doing the example of the how to design an airline as a system.
Okay.
So we were talking about what are the customer needs, and then we had started the decomposition process with stating functional requirements related to customer need, and then the design parameter. And we ran out of time to talk about what folks had done, so maybe if you would like to
Sure.
talk about that.
Okay.
Some of the, we didn't actually hear someone's example. Did anyone have like a 2 or 3 FR and 2 or 3 DPs that you'd like to share? We could look at it for coupling, right?
Well, what's FR0? Do not crash. No.
Well, doesn't it depend upon the customer? That's FR0?
Yeah, see, that's one of the problems with making these up is you have to, they're usually thematically driven, and you need to understand whose needs that you're actually trying to solve. So when you have the CNs up there, I'm thinking you're from the passenger. You're a passenger, right?
Actually, we identified lots of different customer groups.
Okay.
We
So-
identified the internal customers to the airline, as well as the passengers, and one group even mentioned maintenance.
Right.
Maintenance support,
So we had society,
societies.
local community.
Okay. Like Worcester just got a new airline at the airport, right?
Well, yeah, local community has different needs, right? They don't want noise, they don't want congestion. So,
Okay. So
different FRs.
let's have one. Young lady.
I have a question. When you're creating the design matrix, you mentioned that you need to have different themes when you're talking about the customer needs.
Yep.
Did you create a different design matrix for each that you have identified, such as travelers, the flight crew, perhaps?
Right. Yeah, so let's explore that a little further. So the question was, it seems that you can have so many different thematically driven designs. How do we know what is the right one to have, right? So you have society cares about the airport. In fact, Worcester just did get a new airline that's coming online, and that's because the city wants to have the economic benefit of it, right? Then the airline itself has its own FRs of profitability and, you know, driving the competition out, market share, that kind of thing, right? And the passengers have their own FRs of being able to go where they want, when they want, with whatever they want to take with them for the least amount of money, safely, right? Have all that kind of things. So I think I had mentioned when I first started, one of the hardest things to do was to figure out what is FR0 for you. And there is no right or wrong decomposition. It only responds to whatever the top level FR is that you're trying to deduce what the answer is. And if you do a good job at defining that, then you do a good job subsequently of laying out with that, how to fulfill that problem, right? So the way that these decomps work, and I think David probably said this, so I might say it a little bit different way. My FR0 is made up of FR1, FR2, FR3. These add up and equal that. Eventually, you decompose this to a point where you can't decompose them anymore. So it might be 3 FRs, it might be 350 FRs. You know, you don't know. But you should say, if I do this, and I do this, and I do this, I get that. And then the matrix comes when we put all these design parameters and we start to figure out, okay, there's an interaction here and there's one here, but nothing there, nothing there, nothing there, one there. So we could explore how far have you gotten? Did anybody, I see some FRs and DPs right there. What do you have? Do you mind?
I have a more,
Excuse me.
general question. Is it appropriate then, when you're looking at a device, right, like a medical device, let's say, and the way we deal with functional requirements and grouping them, so to speak, just for our own purposes to reference them, is we have requirement descriptors, like a column for descriptors. So maybe, I don't know if that's what she was kind of hinting at. Is that appropriate? I mean, we have one big, you know, whole document full of 200, 300 requirements, but within them, in our trace matrix, we have something that's called a requirement descriptor.
Mm-hmm.
And that could be anything from, you know, accuracy to...
Okay, so the question is, you have the medical device spec, right, specification, and you have multiple hundreds of functional requirements that this thing's supposed to do.
No, they're not called functional requirements, they're called requirements by the government.
Oh, they're called requirements. That's very astute.
And then within that, we have functional requirements, packaging, labeling, constraints, and then what else? Performance.
Do they overlap sometimes?
Try not to make them overlap.
We touched on that in our paper that we were presenting Friday, that in the systems engineering process, when the government specifies requirements, sometimes those are a mix of functional requirements and design parameters. And they kind of see it all as, I call it requirement soup. It becomes this big soup of all requirements. And you don't know whether it's a design parameter that they had in mind that they're telling you you have to do now.
Right.
Because it's a requirement.
But your job is actually to get this thing built, right? So you can get it out there, or?
Well, built for safety and efficacy according to the FDA.
Do you use a method by which you try to figure out what all the different requirements are, and then how are you going to fulfill each one of those?
Well, we have customer needs, right? So what I'm saying is, like, when you were talking about customer needs, and the lady asked, you know, how do you go about, do you group your matrix amongst certain needs? And I mean, one example I was saying, is it appropriate to just have a descriptor column and then organize your matrix such that, you know, you're addressing customer needs associated with wearability of the product.
Okay.
Or accuracy
Well, let me,
Appropriate in this.
let me offer this to you. I'm kind of a hybrid professor around this place, right? So I have one foot planted over in mechanical and one foot over in the business school. It's much easier to design a physical thing using this, because the laws of nature tell you where your limits and your bounds are, and you can't violate them unless you have a time machine or something like that, right? When you get into business systems, it's much more difficult, because it's not the laws of nature, it's the laws of man. And so they're subject to interpretation. The laws of nature are not really subject to interpretation, right? You have the basic forces and how you're going to apply them. So when you're looking at this reaction injection molding machine, there's only so many different ways you could fix that thing, right? Because you're trying to pump a bunch of fluid through some tubes and it's reacting a certain way. When I looked at the ABET criteria, my interpretation, where I boiled it down to 4 underlying, could have been 5, could have been 3. You know, I'm just trying to make sense of how can I look at the system so I can operate it more efficiently. And I suspect that you have some of that happening. You have your physical device, but then you also have these other requirements that are not physical. They're legal and they're, right? And I would say that you will be farther ahead by thinking through this process and trying to capture the information using Axiom Design than if you didn't. But will you always necessarily get a definitive answer? No. Will you get the same answer as someone sitting next to you? No, because it's not a physical system, right? It's a business system, it's a set of rules and laws. So one of the issues I had teaching the global operations strategy class, I really can't teach them global operations strategy, right? One of them is thinking about distributing Apple iPhones all over the world. Another one is they're trying to expand a local medical device company into the Chinese market for some of their products. Completely different. And while there are some basic underlying processes in business, right? You have marketing and sales and operations, right? But it ends there, right? Once you start to drill down, it becomes very specific to the case. So if I am a senior level manager, CEO of your company, my Axiom Design decomp is going to look a lot different than the engineer that's working on the decomposition for the device itself. And so that's why it matters so much to get that top level FR0, get that right, because you're going to solve a problem that's not the problem that the company wants you to solve. You solved the problem, but it wasn't going to move the corporate mission forward. And so you need to make sure that you align your solution to what the company wants. So I don't know if that's helpful for me to say those things.
No, it is, but they constrain you with the costs, so it doesn't matter. It's all you know, we want to make us at $5 a unit. So.
Well, I would argue companies that do a good job at this, whether they call it, you know, we all do axiomatic design. We all do it in our heads, whether we call it that, whether we knew that's what it was. But naturally, as a human mind and doing decompositional thinking, we do these things, right? This quantifies it, puts it in a bunch of boxes with X's on it, and there are more beyond the scope of this tutorial where you can start to put measurements and things into it, right? But just to get the general idea, we do these things. The companies that do this the best are the most successful. You look at the Apples of the world, Samsung now, you know, up at the heels of Apple, they have long-term success in understanding the customer needs and the systems that are going to fulfill them. And I guarantee you they have them written down. They may not look exactly like this, but they have them. One of the beauties of axiomatic design is that you can communicate very complex ideas very quickly to a large group of people that they're going to understand it. So for an example, Chris Brown, after the Challenger explosion, was invited down to NASA Wallops Island so that he could participate on a large team where they were doing a design decomposition using a Claro to figure out what makes the space shuttle go up and what's important about it. And so they printed out all of the decompositions for all the functional areas of the space shuttle. There was environmental, there was navigation, there was propulsion, there was Tang, whatever else they had on the thing. And they taped it up all around the room so that the operational people at NASA could see, oh, I never knew that this thing over here in navigation actually affected crew survivability, part of it. I didn't know that the environmental system had this effect on the propulsion. Or didn't have. I used to think it affected it, now I know it doesn't, because they could see from the top, what's the top level FR of the space shuttle? Bring them back alive, right? Okay, so you have the crew survivability. What are the top level underneath that? I don't know what that is. It's probably top secret. They got to kill me and everything, right? So I wouldn't know. Ask Professor Brown, he was there. But the idea is that you take and figure out what the top level FRs are to get crew survivability, right? Have a launch, be successful, go up, go around, bring them back down, have the parachute work, add those things up together, you get crew survivability. Check. Okay, then you take each one of those and drill them down. So now you're making your medical device. You have a lot of that kind of thought process going on. You have to satisfy the legal people, government regulations, you have your own internal quality, you have the physical design part of the thing, you have patient concerns, right? And so you have 4 or 5 different main decompositions that when you add them up together, you get, yeah, we sold 1 million of that insulin pump, or whatever the thing was. Where the CEO, or she is concerned about that top level FR and what are these main problems that I've given the charge to the people to fix, right? And then so it comes to your desk and you have this part of the decomp and you figure out what all the pieces are to add up to what you want, and then all the main decomps add together and gives you, yeah, a successful company product. So from a purely technical point of view, you don't need a Claro to do this. You just Excel, you can do it, chalkboard, you can do it. The problem is you go 3 layers deep and you're done. You can't go any deeper. So unless you have a Claro, you can't really drill down 4 or 5 or 6 layers deep because you don't have a way to expand the matrix to look at the thing. Or you can't expand just a piece of it to see what's happening in it. So when we do it in class and you do a little decomposition for a business problem, yeah, okay, they get a couple of levels deep and it's not so bad, right? I mean, even my poster that's out there, you can see, there's not that many levels in it. It could go much deeper if I started to say, okay, we're going to read from this page in this book on this day in this class. Well, now we're 19 layers deep into this thing. But we don't really care about that. What we care about is, did we hit the big main target areas in that decomposition? And when I look at the matrix, what design parameter is hitting more than one FR that's going to mess me up? So when I change something, I affect something else, like the faucet, or in particular in the medical device field, well, we're going to change the plastic that we're going to make the part from because it's 2 cents cheaper. And then you find out, well, there's something in that actually combines with whatever's inside the device, and now you got a very unhappy patient either because they got sick or the thing melted or whatever happened, right? So it can be very detailed. But I would say what I tell my students is, you can be the smartest person in the room if you have gone through this decomposition thing before you go into your business meetings. What's the problem I think they're trying to solve? What are the 3 or 4 things that we would have to make sure that we did so we could say we solved that problem? And you could do it just on a, good manager, napkin, pencil, sketch it out. You don't have to walk in with a Claro. And so a little bit of heresy. Don't tell them it's Axiomatic design. Because as soon as they think you have a mousetrap that's better than theirs, then they won't play in your sandbox, right? So you can ask questions. Well, what's the function requirement? What are you trying to do? Well, what are the design parameters that will fulfill that, right? Okay, then they'll play. And then build out the matrix. Oh, okay, I think this is how these things interact. What do you think, right? As soon as you try it out the Claro, oh boy, we got something special here. So I wouldn't say that in front of Matt Palver because he wants everybody to buy the Claro stuff, But these are what I've learned about axiomatic design up to this point. Dave Cochran is much more of an expert than me. So you have, we went through half the slides. The next half of the slides are actually slides that came from Professor Brown, and they have to do with specific cases of things that he designed in surface metrology, and you can look at them after the conference, or you could look at them tonight. You could ask him questions on it tomorrow. But I wanted to make sure that I gave it to you so you had it. You have, how are you feeling about what you saw? Was it valuable at all? I threw a lot of stuff. How to look at a business problem, how to look at a physical problem, thinking about interactions and matrices. I know that my approach to looking at the FRs and DPs is more traditional than Professor Cochran, who has his own method about how he does it. But the idea is that the FRs and the DPs, you get them all in the same place.
Question is, I go through this and I get a better understanding of what the hell I'm trying to do with the customer. But when do I actually do the design? When do I actually start as a team, collaborative team, doing brainwriting or brainstorming and trying to come up with different ideas to solve this?
Okay,
When
so,
do I start that?
okay, so it's, for lack of a better way to present it, it's like, Dad, give me the keys to the car, I'm ready to drive today. Well, you might be able to. There are certain rules where we want to be able to maximize the independence, right, all the corollaries that go along with axiomatic design. But in general, what I would do is I would get a whiteboard, clean slate, and take some customer problem you have and get everyone in the room to agree that what you wrote on the board is what the problem is. That's the first thing. And that will take you half an hour, just that alone, trying to get the problem stated. And then you would say, okay, what are the things that we have to do to be able to solve whatever that customer's problem is? And they'll say, you know, quicker delivery, not lose their shipping information, you know, whatever it is, and get them on there. And then once you get those FRs, you know, 4 or 5 or 6 or 7 of them, then you shift over and say, do we have a system whereby we actually don't lose their paperwork? What's that look like? Oh, there's a guy down back, he's got a thumbtack on a wall and it's on a bulletin board down there. Well, when they open the shipping door, it all blows over the shop. Okay, yeah, well, guess we really don't have a system to solve that problem. And you become the coach to get the people that you work with to populate that matrix at a high level. That's what you do with this.
Yeah, I'm saying we have that. Now when do we actually go in and come up with some new gadget or some new artifact or something that is trying to do that, or at least a couple of ideas, or lots of ideas, and then I can just eliminate them using my experience or whatever.
So David can give you his ideas on that. Here's my ideas. After you have enough input from the people in the problem, you'll be able to drop out a new solution or a new way to look at it that you hadn't thought of before. Or you get new information come in to the room or the discussion and say, you know, here's another way we can approach the problem. The idea behind this is it should happen quicker because you're recording as you go, and everyone's in agreement that what they see, they agree is what the problem is. And you may actually have more than one decomposition. You might have 5 of them. If we use plastic, this is what it looks like. If it's made out of metal, this is what it looks like. If we carved a thing out of wood, here's what it looks like. And so you might have 4 or 5 different design solutions, and then you can go back and do some kind of an economic analysis on the thing and say, okay, this is the one we really want to do aesthetic-wise or money-wise. It isn't a magic thing, but I would say that it makes it clear that it's like, oh, we got this hole here. This is the thing we have to figure out how to fix in order to make our thing work better. But until we build the matrix, we build the axiomatic design decomposition and look at the matrix and see all the different interactions, then you could think about it for a month and not move forward. And so this might shorten the time. You want to augment on that?
I've said a couple of things about government policy, so I'll give them a kudo now. The government defines a systems engineering life cycle process for acquiring technology. and it's in the federal acquisition regulations. So for any DoD program, and I'm learning the medical device industry has its own version of that. So I think the systems engineering life cycle has a really nice rigorous process for determining customer requirements. Everything's a requirement. and so there are milestones or checks along the way. And I think the idea of using, so it tells you when to start, you start when you start with the customer. And so the work that we've been doing is to say, where would you apply axiomatic design along that systems engineering life cycle, and where would it be a benefit to address the milestones that the acquisition process asks for. And so I know that that may not necessarily apply in a commercial business that doesn't respond to the government per se, but the milestones are pretty valid. They talk about conceptual design, and so it's a stage gate type design process. And I think it is pretty much applicable to any kind of design activity, starting with the customer requirements. Just a caveat to that is that usually the government's acquisition process assumes that they understand customer needs. So they will state customer requirements that they think are valid, not that have gone through any kind of major analysis. So sometimes it would be good to push back if you can and say, well, we need to do an analysis to validate the need. Their statement of the need.
So are you familiar with WPI? Have you been through the campus at all?
A little bit.
So in the building behind me, there are posters on the wall of projects that the students have done, and they've used axiomatic design, some of which have led to patents. And so you could look at those and see, how did these people look at what the problem they're trying to solve, and then when they ultimately had a result where, hey, we think we got something saleable here, and maybe you could draw some parallel to solving a commercial problem to how they looked at there, because they're only working on these things for part of a year, and they're coming up with innovation where some of them are actually able to be patented. I would also say that, are you familiar with Christopher Brown? Do you know who he? Okay. I would have a one-on-one with him, and I would say, where is it that I make a lot of money with this stuff? In fact, on Thursday, we're going to have a panel at lunchtime. We have 4 people coming in that are telling what they have done in the field to create money for their corporations, little mini case studies. There are 4 guys coming in. In fact, some of them are probably even here already. And so the idea behind it that I would say is, did axiomatic design make it faster or easier for me to get to this better solution than if I hadn't used it? I think that's the question that's appropriate. Because I'm like you, right? I mean, I used to own a business. I owned a factory for a number of years. This doesn't mean anything to me unless it's right here, right? I mean, I want to be able to move forward and put some money in my pocket. All this theoretical academic stuff only goes so far. So there are examples we have on campus, and you can talk to some of the people here that will be able to make the argument that you should be able to arrive at some point where you are better off economically faster because you use the method. I think that's the overall main concern. And then we're going to hear from Rick tomorrow night. You're going to talk about the ski binding he designed, which is potentially industry changing, that he used axiomatic design to do. So you should have the opportunity to meet a few people that could say that they actually benefited from this. My own personal, I have 30 seconds, right? So my own personal take on this is that schools like WPI turn out a great product, right? You got great engineers, But it's very expensive. And there's not a lot of the operational people that run this place looking at how do we save money. They have stupid things, shut the lights off, use less copy paper, right? Let's look at how the actual machinery functions, which is the professors are the machine tool operators, they're working on the students, which is the product being converted. Let's look at that system and see if we can make it more efficient. I would like to see my ideas be adopted in such a way that some college, either not-for-profit or for-profit, actually benefits financially because they go to a one-piece flow model. That's why I'm into this. You know, I moved away from being a welder a long time ago, right? But I still have that whole manufacturing thing going on. And I look at how this place runs, and it's like, yeah, it's really nice. We have nice stuff. But man, it's really expensive. And their cost of operating is going higher than their ability to raise tuition, believe it or not. Healthcare costs, cost of personnel, and everything else, right? And so I'm saying, okay, if I were the CEO of this place and I was responsible for the bottom line, I want to know, is there a more efficient way to do that? I'm going to design it with this, and I'm going to show you how it works, which is what my dissertation was about, actually.
Isn't the quick fix adjuncts then? Let's hire more adjuncts, they're cheaper.
Say again?
Isn't the quick fix for institutions now to just hire adjunct professors?
Well, that's what they do. They do that in other states that are south of the Mason-Dixon line. They do that. No, that's not, you know, this thing, you know, the MOOCs that are coming, the Massive Open Online Course, it's just a tool and it's just a method. Is it going to replace the residential college like we have here? There's no way. There's so much more that the students gain in their education in addition to the factual information. And so the adjuncts don't do basic research necessarily that move everything forward. The problem is that there's so many inefficiencies that could be eliminated, and it's because it's not viewed from, it hasn't had to be viewed from that point of view. It's coming, right? Government pressure, student pressure, loan defaults, right? And so the colleges that react will be around in 10 or 15 years, and the ones that don't will look very different than they do right now. And the problem is going to get solved because it's either going to be solved in the United States or someone outside the United States is going to solve it. And the students will go there. So one way or another, it's going to get fixed. I know the dean of the business school is consulting to an engineering school in South America that has all brand new facilities and has no debt, and you can get an A-BET accredited degree for 20 grand. Okay, so at one point, yeah, fun, you know, if you're MIT material, they're always going to be there. You're at the state college material engineering program and kind of in the middle to the lower part of the pack, I might go to South America. Right? So those competitive pressures are going to come on the system, whether the system wants it or not. I mean, it's happening already.
Small question. You introduced this FR0.
For me, it is kind of new. I didn't know this before. Do you also how do you define DP0? How you formalize DP0?
Yeah. So let's say your FR0 is leave Wally's lecture by 2:35 p.m. The DP0 is system to leave Wally's lecture by 2:35 p.m. You can take the FRs and restate them as a DP, say system 4.
See, so the word system, it is complexity of
Yeah, or method, or solution for. So what you're saying is, okay, I have this very complex problem that I define as my number one thing I'm trying to fix. And then the way you fix it is, okay, there's a system that we developed that fixes it. So then as you come down through the FRs, you have corresponding DPs that respond to each one of those. Yeah, system to get out of Wally's class by 2:35. And then if you stood up, walked out the back of the door, and you had 1 minute to do it, you add all these things up, that's the system for you to get out of here by 2:35. And would you fulfill FR0? Yes, you would do it. And so we're 4 minutes over. Go ahead.
You have a corollary, each functional requirements requirement requires a design parameter. But in the case of a smartphone, if I take components, I could satisfy various requirements. Could I arrive to a smartphone by applying axiomatic design? Because smartphone, if I apply your corollary, is uncoupled, is a coupled.
Right. So some coupling is negative. If something's coupled, it's like that's bad. Some coupling is not negative. So when we looked at the example of the engineering school, there was a lot of coupling in the A-bet requirements, but they didn't affect things negatively. It's just that they may cause inefficiencies. So can you have a DP that satisfies more than one FR and not have it being bad? Yes, you can do that. I have a cell phone, which is also a camera, right? So I have two. Are they independent? Oh, so let me just check myself, right? So I don't say something that's incorrect. Physical integration is different than functional independence. So the phone can be a camera, it can be a phone, and it can be a whole bunch of other things all at the same time, and neither thing has a negative effect on anything else. So can you have it all be contained within the body of that phone? Yes, you could do that. Professor Cochran, was this fun?
Oh, yeah.
All right, I'm keeping you, so thank you.